Let's examine this Fibonacci recursive function. The code is nice and simple, and if we compile Fibonacci 5, or with an argument of 5, we get 5, it works just fine. And if you look at the execution time, you get it in 5 seconds. If we compile it with 10, with an argument of 10, it's still pretty good. You get 55. And let's double that. Let's go 20. Still 3 seconds. And let's go 30. 0.4 seconds. So far so good. Let me enter 40 as an argument and let's run this. Two seconds. So the time is going up, but it's still pretty reasonable. Let's try with an argument of 46. $11 seconds. So as you can see, the execution time is taking longer. This time it took 11 seconds. Let me just do 47 and see how long that will take. So it took 17 seconds and we're getting some kind of negative. And so what's happening is our stack frame memory can only handle so many stack frames that it eventually produces weird numbers because we have either an error or we get into the stack overflow. But as you can tell, 17 seconds for 47. So that's what is meant by having a time complexity of O of 2n. In the beginning, we're okay. You know, at 5 or 10 or 20 as an argument, we're okay. The time's reasonable. But as we go higher in numbers, the time complexity takes longer because it grows exponentially. Even though this Fibonacci recursive function is simple, clear, and easy to read, it's very expensive because it accumulates redundant stack frame calls in our memory. If you look at our tree, for example, let's take a look at f of 2. F of 2 is called 1, 2, 3, 3 times. If you look at f of 3, it's called 2 times. But from this parent root, f of 3, it calls 1, 2, 3, 4 other stack frames. Also, if you look at the values of f of 3, we know that it returns 2. We know that this returns 2. But they call, so f of 3 will call 1, 2, 3, 4 other stack frames, and that is way too expensive. And that's why our time complexity, as we get into a higher argument, and this is just a 5, imagine how many children the stack frames will generate when we have 46. I don't even want to draw that tree. As you can see, this algorithm is inefficient because we keep doing things repeatedly. Like for example, F3, we do that repeatedly. F2, we do that repeatedly several times. And this is just F with an argument of 5. Imagine how many repeated things we would do if we had an argument of 46. So is there a solution to improve the efficiency of our algorithm? The answer is yes. If we look at our tree, notice how F3 has the same values. F2 has the same value. They're all 1. And obviously our base case has the same value. So based on that, we can save some time by storing into some form of data structure. For example, we can store F3 into some form of data structure. Then we wouldn't have to call it here where 1, 2, 3, 4 other stack frames are generated. Likewise, if we can store F2 in a data structure and the value of it, or what it returns, we can save 1, 2, 3, 4, 5, 6 stack frame calls, or function invocations. And this concept is called memoization. So the idea behind this concept is to store the values for recent function calls so that future calls do not have to repeat the work. So let's start coding our new Fibonacci function so that we can optimize it. And here I'm going to create a function prototype, and we're going to call it Fibonacci underscore M for memoization. And then we're going to have a parameter of an integer data type. And I'm going to put it above this previous function. All right, so the first thing I want to do is I want to target our base case. What we want to do is we want to say if data is 0 or data is 1, we want to return data, but we also want to store that data in an array. So let me declare a global array. So above main on line 20, I've declared a Fibonacci array, and I'm going to give it the size of 46, since that's the farthest I want to go. For this tutorial, 46 is sufficient. Or actually, let's go 47. So back to our code. So if data is 0 or 1, then we want to store that data into our Fibonacci array data. Let me illustrate that by drawing an array on the right-hand side. So here we have our fib array. So for lines 35 through 37, the idea behind it is we want to store f of 0 into fib array index 0. And likewise, we want to store f of 1, which is 1, into fib array index 1, and so on and so forth. Once we figure out the return value for f of 2, we want to store that into index 2. And once we figure out the value for f of 3, we want to store that into index 3. So after storing data 0 and data 1 into fib array index 0 and 1, we then want to return that data. Now let's go into our recursive case. For our recursive case, if you look at our original Fibonacci function, we simply return data minus 2 plus data minus 1. Well, what we want to do is we want to store data minus 2 into our fib array. But how do we know when to store, for example, f2 into index 2? What if there's already f2 in there? We can simply override that. And once we discover the value of f3, how do we know when to store to index 3? We don't want to override if we've already stored a value in there. So a solution to this would just be to simply initialize our array. We can make them all -1. For example, if index 2 is -1, then we know we haven't stored f2's return value in there. And so if it's -1, then we'll store the value in there. And if it's not -1, then we'll leave it alone. And here on lines 25 to 29, I went ahead and created a for loop, which initializes every element of the array to -1. And that's the reason why we wanted a global array, so that all of our functions can have access to it. Another way to do it is to create a static array so that you don't have to make it global, which essentially gives our functions access to that data type. But let me go ahead and test this and do a printout of each element. And so it's just going to be the same for loop. And I'm going to comment this because we don't want that to run for 17 seconds. So I went ahead and copied and pasted our for loop. And the only difference is that instead of storing -1 to all the values, I'm just printing all the values. And so let me run this. And so there we have -1 for all of our values. And I really won't need this, so I'm going to go ahead and delete that because we know that we have a -1 stored in all of our values. And so now let's go back to our function. So again, for our recursive case, I want to be able to store data minus 2 and data minus 1 into fib array data minus 2 and data minus 1. Here what we want to say is else if fib array and then data minus 2. If data minus 2 is -1, that means that we're not going to overwrite anything, so we can store our function value or function return value into that index or into that array index. So we want to say fib r data minus 2 and assign our recursive call data minus 2 to that. And likewise, we also want to do it for data minus 1. So the same exact algorithm. So if data minus 1 is -1, then we can override that index and store our fib array data minus 1. And we want to go ahead and assign our Fibonacci data minus 1 to it. Let me make a comment here. Assign function values to array index. And then after that's done, all we want to do instead of returning the recursive functions, we're just going to return our array. So we're going to return fib array data minus 2 plus fib array data minus 1. So notice how in the original recursive function, we're returning a Fibonacci recursive call and adding it to another Fibonacci recursive call. Whereas our new function, we are returning 2 array indexes. Let's test this. So the first thing I'm going to do is I'm going to run our original function again. And this time I'm going to use 46 and then print it. And notice how long the execution time took. It took 11.114 seconds. Now I'm going to run the same argument of 46 with our new function, the Memoization, and I'm going to compile it. Notice how it took 0.027. It's basically linear time. Okay, now let's run it with 47, and this is where it gave us funny values with the original function. And I think it gave us a negative. Notice how the execution time took 16.635 seconds. And the return value it gave us was negative 1323. So it's giving us funky values. Now let's run it with our other function. And notice how, again, a lot less time, 0.029 seconds. And it's significant. And here's the value, 113449. So I think what this tutorial has shown you is that although a recursive function is eloquent, easy to read, simply written, less lines of code, this tutorial showed how this function can get very expensive, and the time and space complexity of big O of 2n or 2 to the n power, that's just way too long as far as time complexity. And we can optimize this recursive function by storing function return values into an array. So in summary, memoization is the concept of storing values for recent function calls so that future function calls do not have to repeat the work. It's a good way to optimize time complexity. Now space complexity will still be O of n because we're still using the stack frame with this function, but it at least optimizes your time complexity. So again, our time complexity goes from big O of 2 to the n to big O of n. So as far as space complexity, it's still going to be O of n. There's not going to be much of an improvement from the original recursive function to the optimized memoization function. Space complexity is basically any memory you use, like the call stack. Even though we're not using as much call stack in the optimize function, not all of the functions or not all of the recursive functions are on the call stack at the same time. So we can only have O of n on a call stack at any given time. Thank you for watching.